The transient process. In previous section, we considered the steady state process and several examples of its application. Many processes of interest in thermodynamics involve unsteady flow and do not fit into the category of the steady state. A certain group of these, for example, filling closed tank with a gas or liquid, discharge from closed vessel, discharge gas or liquid from closed vessel can be reasonably represented to a first approximation by another simplified model. We call this process the transient process. For convenience, recognize that our model includes specific assumptions that are not always valid. Our transient model assumptions are follows. The first assumption is the control volume remains constant relative to the coordinate frame. The state of the mass within the control volume may be changed with time. The state of the mass within the control volume may change with time. But at any instant of time, the state is uniform. At any state of instant of time, the state is uniform. Throughout the entire control volume. Or over several identified regions that make up the entire control volume. The Part 3. The state of the mass crossing each of areas each of the areas of flow on the control surface is constant with time. Although the mass flow rate may vary with time, although the mass flow rate may vary with time. Anyway, we have three assumptions here. Let me the control volume remain constant relative to the coordinate frame. The state of the mass within the control volume may change with time, but at any instant of time, the state is uniform. It means that, for example, if we have considered this point, we have always some properties of flow in this point, but maybe the state change, for example, from point to point. The state of mass crossing each of areas of flow on the control surface is constant with time. This is also say that this state is uniform, is constant, but may vary with another section in a pipe flow, for example. Let us examine the consequence of this assumption and derive an expression for the first law that applies to this process. The assumption that the control remains stationary relative to the coordinate frame has already been discussed in the previous sections. The remaining assumption leads to the following simplification for the continuity equation and first law. The overall process occurs during time. At any instance of time during the process, the continuity equation is or dmCV on dt plus m dot e plus minus m dot I equals to 0, where the summation is overall the area on the control surface through which flow occurs over all areas that flow occur during time t. At any instant of time during the process, the continuity equation right as this relation, where the summation is over the areas which flow occurs, integrating over time from this relation will give us from 0 to dm control volume on dt m2 minus m second, because the total mass leaving the control volume during time is total mass leave is the integration of, for example, m dot e dt, which is equal to sigma m e. M dot is dm on dt, and the total mass entering Therefore, for this period of time t, we can write the quantity equation as this relation. Here we have the left hand relation here and right hand of the continuity relation here with this integration. Continuity equation for transient process is the m second minus m1 on the control volume plus sigma m e minus sigma m I equals to 0. For example, a tank have a entrance pipe here, so m1, and in the second is discharged to, for example, m second from this or this port. Anyway, we have and we have me only and mi, for example, here. m2 and m1 denotes the second quantity of mass in the control volume, and m1 in the quantity of the fluid in the control volume, and the sigma me is the total mass entrance and total mass exit and total mass entrance. In writing the first law, so we have continuity, and for the first law we have this relation for the first law of thermodynamics, the control volume on dt, the inlet Q minus outlet W plus sigma m dot I hi bi second and gzi minus sigma m dot e HEBE second plus GZE plus it is control volume Q dot and W dot on control volume. Okay, so we can write this relation again. Q dot control volume plus sigma n dot I h I plus v I to g z I, this part and this part, equals to the dE on dt plus sigma m dot E W control volume. Since at any instant of time the state within the control volume is uniform, in any instant of time the state is uniform, so we have this relation for E control volume equals to U plus N 1 second M V second M G Z or N internal G Z of the control volume. Replacing to the relation before, we have this equation for the first law plus m dot I h I plus m dot E h E plus W control volume and plus the transient for M U plus V2 GZ of control volume. Applying integration to this relation, the first part dt is Q on control volume, the integration of mi hi plus dt equals m hi plus for the m dot E h E h E and W dot control value dt equals to W control value, and the last step transient part is important and is dt is equals to the m second u plus v2 vz2 u1 control variable. Therefore, for this period of time t, we can write the first law as this relation. Q on control value plus sigma MIHI plus W control volume and plus the second state of the control volume with mass for the transient process. An example also available in the video part related to transient processes. The next section in engineering applications.